Yeah, it'll be kind of homework style. I was going to talk a little bit about the final today. I don't want to post the notes or the code that I'm going to write up today, but I'll have this video being recorded so you can kind of watch there. But I don't want to actually share too much. Okay. All right. So I want to talk a little bit about. We'll talk about k-means clustering. All right. And so I'm gonna, yeah.
Are you gonna post the notes from earlier this week?
What were the notes from earlier this week?
From Monday and Wednesday?
I don't think I had notes on Monday though, or did I? Wednesday? Okay. Sure, I can post those. It was kind of like this is what our class was all about though, right? But yeah, okay, we can do that, no problem. All right, so let's talk about k-means clustering. What we're going to do is we're going to load up the library for multivariate norm. Okay, so this is a library for multivariate normal distributions. And then we can make a covariance matrix. I'll call this covariance M, all right? And, this would be, for two variables, this would mean that x and y are independent, right? Because there's no covariance here. And so, I can make some clusters, and I would use the function random multivariate normal. And let's say we want to join, have 100 values generated at random. My mean we're going to have to be coordinates, so we can have it centered at say 3, 3, and my sigma matrix will be the covariance matrix. Okay, so here's J, and I can just I can plot J here, and there's some multivariate. This is a random Gaussian centered at 3. You know what? Let me set a seed here. So we'll do set seed 1. Okay, and then we can plot J here. Okay, so that's set seed 1. We can do another cluster. We'll call this cluster K. And we can use the same covariance matrix, and we'll just pick a different center here. Maybe I'll pick the center 5, 8. Okay, and then we'll pick out the points 8, 3. Okay, so I've got J, K, and L, and we'll bind all of these together. R bind J, K, L. This will form our data matrix. Okay. And then our groups, this will be make a factor, and we're going to repeat J 100 times. Whoops. Repeat K 100 times, and we'll repeat L 100 times. Okay, and then let's plot our data. Okay, this is what it looks like, and then we'll color the points based on the groups. So there we go. Okay, is that so far so good? Okay, and so your job, so you will have to write up a k-means clustering algorithm. All right. Okay. So that's it's not too bad, right? So we have a few ways to do this. First, we're going to randomly assign our points to clusters. All right. So we'll do we'll create a vector called assignments, and basically what we want is we have 300 data points, right? So we're going to just randomly sample from J, K, and L. Am I doing this right? 300 and replace equals true. Okay, and then so if I look at assignments, okay, I've got a bunch of these, right? A bunch of these things I should do as factor, right? So I'll do we'll make a factor of this, and our levels will be J, K, L. Here, I'll split this onto 2 rows. Okay, so we're going to randomly assign our things here. Okay, and we can look at our assignments there. And so at this point, if I plot my data, and my color will be my assignments, okay, we see, it's all over the place. So that's kind of where you get started. And then what do we do? You got to calculate the centroid of each of these things, right? So we calculate a centroid for each group. Okay, so this is the part you've got to come up with. I'm not going to do this part for you. Okay, and then once you calculate the centroid for each one, then you reassign the values to the nearest centroid. Okay, so use Euclidean distance. And then iterate. Calculate the centroid again. Reassign the values. Okay. Iterate. You stop when no assignment changes are made. Okay. So it's probably good to have somewhere in there, old assignments and new assignments. And then you want to do a kind of a comparison to see if there's any changes. If there's changes, then your new assignments become your old assignments, and you run the loop again. Right? Does that make sense? All right, that's k-means clustering. That's going to be your manual, okay? And then I will show you how to use the built-in k-means clustering. So I think it's good exercise to have to code this yourself, okay? And then, but if you ever have to do k-means in real life, it's probably better to use the professionally built k-means code, okay? In general, that's if an expert has done it, it's probably pretty good, because when it goes into production, you have thousands of people running the code to make, so if there's bugs, we can do it, okay? So in this case, we would just do k-means on our data. Here, let me pull up the help for k-means, okay? The arguments is your x, which is a matrix of data, okay? And then you'll give it how many centers we want, and then the number of starts, okay? And so because in this part where we do our random assignments in the beginning, okay? We're sampling JKL kind of randomly at the beginning. Sometimes, depending on the initial assignments, you end up getting different different findings, okay? And so you have the option of having like multiple, like starting this over, 10 times, 20 times, and we kind of measure how good the fit is by measuring the total within sum of squares, okay? So what is the total within sum of squares? That is going to be, each cluster has a centroid, right? And so you can calculate the total squared distance from the centroid. And so, after the end, every data point is assigned to a cluster, and we want to minimize the squared distance to each cluster center. And that's going to be the total within sum of squares. So here, I can just write k-means dat, and I can say centers, we want 3 centers, and our, we can, here, I'll just do one start here, okay, and this is kind of the output. So we'll call this results, all right? And so let's look at the structure of our results. So we'll run this. The structure of our results, we've got cluster and centers and all of this. So what I can do is I can plot our data, and then our colors will be equal to results $cluster. Okay, and it looks like it did a pretty good job. If we did compare this to the true groups, which I think is under the variable groups, okay, because we can see if any of these kind of points in the middle are incorrectly classified, and it looks like this one gets classified as here instead of the actual one of belonging over here. But overall, pretty good. Okay. Yes.
What is the argument n start do again?
N start.
Yeah.
This is so what it does. So here I can do like 10. Okay. And what it does here, it's going to look the same. But let me just show you what happens. Okay. Let's say I do 5 clusters. Okay. So 5 clusters is probably too many. Right. So here, let me plot this, and it's found 5 different clusters. Here's 1, here's 2, 3, 4, and 5. It's found 5 different clusters based on this. Now, if I run this again, and I plot the results, here it found 1, 2, and then it found 1, 2, 3 clusters here. Okay. And then, and if I did this again, it split it this way. And it's all because of kind of the initial random assignment, and here it splits this. So when this is generally more of a problem if you've got kind of the wrong number of groups. But so when you do n is equal to something like 10 starts or even 20 starts, what it does is it finds all of these different things. For each of these different results, what it tries to do, or what it does, is it calculates the total within sum of squares. Okay. So here, let me just do this again. So here's 1. Here's the results there, and we look at results, and there's something in here that's total within sum of squares. Okay. The total within sum of squares is 500.8916. Actually, I'll put that in here. I'll say main is equal to results total within sum of squares. Okay, so here's one thing. The total within sum of squares here is 494.369. If I run it again, here I get a total within sum of squares 501. Over here I get 491, and you know, we're getting different things. And so with n is equal to like 20 starts, I do basically 20 different things, and I'm going to pick the one with the minimum total within sum of squares. Okay, and so in this case, the one with the minimum total within sum of squares is 491.398. Yeah. Whereas, you know, if you have specified the correct number of clusters, you know, this is going to be fairly consistent every time we redo this. Okay, we see that we're getting the kind of the same results every single time. Of course, because of the random assignments, you know, there's label switching. Okay, this is called label switching. You know, this one's called cluster 1, cluster 2, cluster 3, and then maybe in another one, this one's cluster 1, this one's cluster 2, and cluster 3. It still finds the same clusters, it's just we've called the labels of the clusters different things. And that's fine, no problem there. So anyway, this is how we use k-means. What we can do is we can kind of keep track of our total within sum of squares, and we can see how the total within sum of squares changes. So if I only have one cluster versus 2 clusters versus 3 clusters, we can see how much the total within sum of squares changes. And you know, when we go from 1 to 2 to 3, there's dramatic shifts in our the number of clusters that we find. Okay, here we can do 20 starts for each of these. And here, let me just do a loop. For I in, we'll say 1 through 10, we can run k-means, and then we'll call this SS. We'll start off with SS0, and we'll do SS sub I is going to be this, and we're gonna change the number of centers from 1 to okay. So let's just let's run this, okay? And we can see kind of our results for sum of squares, and we can see, you know, it drops off dramatically here. So let me just do a plot of SS. What do we want? Type dot L. Okay, and we can see, or maybe I should okay, we can see, you know, there's a dramatic drop when we get to 3 clusters, okay? And then after 3 clusters, you know, adding more centers is going to reduce the total sum of squares, but we can see, you know, the kinds of improvements we get is much less. Okay, and so when we look at this, we're kind of like, okay, 3 centers probably seems right. You know, kind of, I mean, obviously looking at our plots, it seems like 3 does a better job than anything else. But you know, here we had very nicely separable clusters, all right? And in other cases, you know, if our centers were a lot closer, let's say we did 3, 3, and then I go to, you know, 4, 5, and then 6, 3, okay? Okay, it's a lot more messy, and so when I do k-means clustering on this, with doing 3 centers, we're going to get it a little wrong. Okay, so this is what k-means finds, but we got a lot of mixing in here, so it's gonna be off. But that's how k-means clustering works. Okay. Let me talk a little bit about the what you'll be doing with the EM algorithm. Okay. And I found I found a handout that I think does the EM algorithm kind of explains it a little bit nicer for coding it up than you know. I think our textbook does a good job of explaining the EM algorithm. I think what. I think this handout does a good job. You know, it changes one of probably the biggest change is that they use W instead of Q. In our textbook they use Q, NK. Here it's W sub IK. All right, and I hope that switch is okay. And then they use, I think our textbook uses pi, and here they use alpha. But conceptually it's all the same, okay? And so I think, in my opinion, these equations for, you know, computing the membership weight and then using that to compute your, you know, your mixture weights and each of these things. Is I think it's a little bit better. So I'll post these notes up for you guys, and I'll also include some notes in the final exam itself. Okay. So you know, what you're going to have to do is you're going to have to go from kind of the math equation of what we're doing into the you know, kind of the coding of itself. And so the big idea here for the EM algorithm, you know, we're going to have different clusters, but what you've got to do is you're going to have to calculate your weights. Okay, kind of the your expected weights using Bayes' rule. Okay, so this is similar to your Bayes classifier. All right, so you know, in the numerator has the kind of the likelihood of your data given a cluster membership multiplied by times the kind of the prior probability of that cluster, which is the relative size of the cluster. Okay. So that's going to be the numerator, and of course the denominator is what? The sum of the different numerators for each cluster. Numerators. Okay, and so to get the likelihood of your data, all right, we're going to be dealing with two-dimensional data, and so, you know, rather than having to compute the normal density for a multivariate normal, to get the likelihood, to find the likelihood, you can use the function dmv norm. Okay, so in your Bayes classifier, you use dnorm, right, to kind of compute your likelihood for the normal distribution for, you know, your petal length and sepal length or whatever those things were. You use dnorm. Now that we're dealing with a multivariate norm, just go ahead, make your lives easier, and use density for the multivariate norm. Is that okay? So, so you can use dnorm. Usage is similar to using dnorm. Okay, but it's multivariate. So let me just kind of demonstrate. You would do a dmv norm. Here, let's pull up the help there. You're going to just say, okay, let's say my data point is the data point 3, 3, and our mean is equal to 2, 2, and my sigma matrix is equal to what did I have? At this point, we'll just use covariance, the covariance matrix, okay? And so here it calculates the density of that point, and we can see that if I draw if the data point is far away, at like 7, 8, the density for that is really small, and the closer I get to the mean, the data the density gets higher, right? The likelihood for that data point gets higher. And so this, if we wanted to graph this, it would be a 2-dimensional surface over the over the 2-dimensional space, right? So anyway, you would use this like this. You do this. This would be your likelihood term. Okay. What's our prior probability term? Okay. So at some point you've calculated weights earlier, right? So the prior probability term, this is kind of our alpha. Here we would have to do kind of this would be the sum of, ideally, if we had deterministic assignments, it would just be the count of points in cluster 1 divided by total number of points. Okay? But now that, because it's probabilistic, our assignments are probabilistic, right? We're using a Bayes classifier. Probabilistic. Okay? It is the sum of probabilities of belonging to cluster 1 divided by total number of points. Okay. So that's going to be kind of your prior probability term that you'll do. Okay, you multiply those two together to get your numerator, and then you'll add everything up to get your denominator, and this is going to be your expected cluster assignment. Okay, so multiply these terms in the numerator, okay, and then sum across clusters for the denominator, okay, and then you'll get a vector of probability assignments for each cluster. Okay, so this should be reminiscent of your naive Bayes classifier. Is that okay? So you should have something similar to that. Okay, and so that gives you your expected classifications, and then once you have your expected classifications, then you calculate basically a maximum likelihood estimate of the mean, the centroid, which is done very similar to k-means, except you're weighting each point by its assignment. And then you find a maximum likelihood estimate for the covariance matrix, much like you would do. And then based on that, you would redo your expected assignments, and then you'd redo your maximum likelihood estimates. Okay? So in the naive Bayes classifier, you did your maximum likelihood estimates in the beginning, and you use those to get your classifications. Here, we're iterating back and forth. We kind of just start off with some points. We get we use our Bayes classifier to get probability assignments of each cluster. We use that to get maximum likelihood estimates. We use those things to update our assignments. We go back, we get new maximum likelihood estimates. We go back, we update our cluster assignments, and we go back and forth. And that's the EM algorithm. The E is updating the assignments. It's the expected assignments. The M step is getting your new maximum likelihood estimates. Do we feel like we can get a handle on this? Some of you are shaking your head. I think you will surprise yourself at and say like, wow, I did this, and it'll feel good. I mean, there's always a possibility that it's hard, but I think it will be a good. I think it's kind of fun. Coding up your very first EM algorithm. That's kind of your you get your little badge for your statistics scouts. Okay, after that, all right, and I will include some instructions for using support vector machines in there. I'm debating whether or not I want you to do like the manual version of a support vector machine, or if we should just go straight into the packages. I'm kind of as I write this, I'm trying to figure out how long it would take me, and then I multiply that by 3. Yeah, I was doing like 4.5, and I figure, okay, well, if it takes me this long, I'm estimating the student will take this long, and that's kind of how I'm gauging how long the thing should be. So I'm kind of giving myself like between 90 minutes to 2 hours to code up the whole thing myself, and I figure if I can do it 90 minutes to 2 hours, it should be the appropriate length for you guys to do it in by Wednesday. What? 11 p.m. we said? All right, for your undie run. Okay. Anyway, a lot of you guys I get to see next quarter, and I'm excited about that. Some of you guys, this might be the last quarter I get to have you as a student. So it's been a great pleasure being your teacher. I hope you enjoyed the course. If you have it in you, leave a review at your student evaluation or Bruin Walk. And so good luck to you all on finals, and we'll see you guys see you later.